So I'll give an introduction to assembly theory in a moment, but just the motivation for this talk is coming from looking for biosignatures uh, in in space, like in the solar system, but also further. So like looking at exoplanet atmospheres, but also in situ measurements in the distant solar system and on Mars. And we kind of have this problem that there's not any observation we can even in principle make that we know how to reason about and say that, yes, that's definitely life. Because in a physical sense, we don't definitely know what life is as we don't know it, right? And so the problem is basically that our current definitions of what life is are these post hoc justifications for how we understand the way we categorize our own biosphere and our own world. And if we want to have some sort of explanation that generalizes outside of this biosphere, we need some, physical explanation that is not based here, right? So the kind of basis of this idea is thinking about defining life by what it does. And we're taking two properties. So the integration of historical contingency. So you can think about that as also like the integration of like broken symmetries or frozen accidents, whatever you'd like to call it, but then also the creation of complex objects in high abundance. And so in assembly theory, we're starting with the observation that all material complex objects are constructed with reused motifs across scale. And we can use those reused motifs to reason about the historical contingency that's inscribed in the physical structure of these complex objects. So to take a comically simple example of a complex object, say 7, the number 7, and we're going to build it from some substrate, just ones, by the operation of addition, right? We can say that 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 2 is 4, and 3 plus 4 is 7. So we call this like an assembly path, and this one has a length of 4 because I use 4 binary joining operations, in this case addition, to get from my units 1 up to 7. And when we consider some class of complex objects in this framing, we end up putting them in something that we call like a combinatorial space, where you have the very simple things that you can build right away at the bottom. And as you add more and more steps, you can build higher and higher up in this space. And the space is growing incredibly quickly, such that if you are a real system, you have finite material, and you're building things without much discretion, you're diffusing your material out over this combinatorial space incredibly quickly. And so you will not be able to build any individual complex object in high abundance. But we know that life is doing something necessarily very different. We are building many, like even at the molecular scale, molecules that are far too complicated to be enumerated here on Earth, but we're building them in high abundance. And so we're focusing on this property as a potential physical definition for life as a phenomena. And so the first interesting substrate that the universe encounters that actually has the capacity to host this sort of combinatorial complexity is chemistry. And the way we break down chemistry is we say, so these units are going to be just chemical bonds, single bonds. That's what we're going to build everything from. And we're going to count for a given molecule, say this one in the black box in the top right, we're going to count how many joining operations does it take to get from these units up to there, where I'm taking 2 fragments I already have access to, and I'm combining them together by identifying some of their atoms. And so in the case of this molecule here, we would say that this happens to be the shortest path to build it. And so the assembly index of this molecule is the number 7. And so this isn't a terribly complicated molecule, but when we go to larger ones, say like this one here, this one on the far right takes 14 steps to build, has an assembly index of 14. It's a really interesting question to ask, like what does it actually mean about your system if you observe this thing in high abundance? So this is a pretty complex molecule in that you could not, with any reasonable amount of material, enumerate the molecules of assembly index 14. So something special is happening here that my system has this molecule in it in high abundance. And what this way of breaking down the construction or the assembly process of it this way allows us to understand is that this assembly index is an approximate lower bound for the number of constructive operations my system needs to physically encode to make this observation true. So like these molecules are subject to thermodynamics just like everything else. And so they decay. And so if they're going to be present in high abundance, they need to be continuously constructed. But like we've talked about before, through an undirected diffusive manner, you just will not get anything this complex in high abundance. So that's the basis for like the physical motivation for assembly index as a complexity measure. But another thing that's really important about it is that you can infer it from experiment, preferably in an agnostic fashion. I don't want to have to know what I'm putting into my machine when I measure it to measure the assembly index. And it's maybe not too surprising that something like this is true. So if I put a really high assembly index molecule into a mass spec, the amount of fragments I'll see in that mass spec is going to be a lot larger than if I put something much simpler with a much lower assembly index. And so, I mean, you can do this in a myriad of ways, but obviously you can get pretty good correlations out of it and make inferences about what the assembly index is of your material in a substrate independent fashion. And when you do this for a bunch of different samples taken from around Earth, what you find is that if what you're looking at is abiotic, there seems to be some kind of complexity threshold, some assembly index threshold beyond which you stop finding matter. And so in the case of some experiments that have been done in the past, that these abiotic samples happen to peter out at around assembly index of 15, while biotic ones can go far beyond that, even double. And so this is a really promising empirical result for like building some biosignature that's free of false positives. But though the way we reasoned about assembly index isn't really based on anything we don't expect to generalize, these experimental data are, right? Like these are just taken from Earth. And so to actually be able to generalize this result beyond Earth, we need to have some understanding of why this is happening. And that explanation needs to also generalize beyond Earth. So the way we're going to attack this problem, and I'm not going to claim to have solved it, but part of it, is that we're going to try to relate expected path length, expected assembly path length, and thus the number of operations I think my system's actually encoding to build these things, to selection. And by selection, I mean something very general. So we're treating a priori all these different joining operations kind of on equal footing, and we're looking at the combinatorial structure to try to like elucidate things about object complexity. But we can perturb those assumptions and say, well, what if we have some preference for certain joining operations? And this is what I mean by selection. So this kind of non-uniform treatment. And so we're going to talk about expected path length by taking some object. So in this case, like say this molecule here, and we can just sample from the different assembly paths to build it and get an idea of what that distribution looks like. How many paths are of a given length, this sort of thing. And so, for instance, for this molecule here, if I have absolutely no selection whatsoever, I should expect to find a priori an assembly path for it of length 84. And these paths can range at the low end to the assembly index because that's like the shortest path it can be. And at the high end, in this case, the number of bonds, because you need to add at least one bond to the thing every time, right? But what we're going to do is imply some more constraints, the selection onto this distribution to shift it and talk about how the expected path length is changing as a function of our model of selection. So first what we'll do, and to make it more straightforward, we'll just talk about coming back to like numbers again, like integers. If you take an ensemble of objects, in this case, like 2 to 100, and you bin them by their assembly index, so this is on the x-axis here, you can look at how their path length distribution varies as a function of that. And so this dotted line on the bottom, that's like the assembly index line. And this white solid curve, that's the average path length. And what we find is that that is pulling away from the assembly index exponentially. And that's physically meaningful because if you think about yourself as a complexifying system, that means that as you move up steps in this assembly space, you're going to be, if you have no selection, you're going to be needing to encode an exponentially increasing amount of joining operations. And that's a physical process. No finite system can do that in an unbounded way. So we can hope to find some physical constraints here. So talking about actually applying selection, we'll just talk about a single distribution here. So this darkest curve, we're talking about just the number 100, no ensemble anymore, just one object, 100 built from 1 by addition. Those assembly paths are this darkest curve, this parabolic shape. But we can apply selection to this, and the model we're going to use here is thinking about selection as some probability that evolution can append a new operation to a path. So if I'm thinking about an assembly path, the right time scale to be thinking about is not some materialistic one. It's not on the life of the time scale of a lifetime of a single organism. It's evolutionary. Like this is an innovation-like process that's happening. So if our model of selection is saying that sometimes evolution can explore all these paths, and it hits dead ends, and we have some uniform probability for how those dead ends are placed. This is what we're talking about. And so this selection coefficient is what's going to scale that probability. So when that's 0, this probability is 1, and it's like that unperturbed distribution. But as we increase the selection coefficient, we're lowering that probability. We're making it harder for evolution to build these complex objects. And the effect of that is to favor these shorter paths. So on the far left, there's this green dashed line that's the assembly index. I think it's 8 for 100. And as we apply more and more selection to this distribution, the expected path length is shifting over to the left, closer to assembly index. And so coming back to an aggregate of objects, we can again take the integers 2 to 100, bin them by their assembly index, and ask, how did their expected path lengths change as a function of this selection coefficient? And so there's 2 interesting limits. So in the low selection limit, that's this dark curve on the far right, we're pulling away exponentially from assembly index, from like the theoretical optimum. But in the high selection limit, these yellow curves here, we're keeping linear with it. And so that's kind of half the story in terms of finding some abiotic limit, right? So what we've done is we've related selection to expected path length, like how much operations my system needs to encode to make this observation true. But we don't actually have some sense yet of how many operations my system can encode. Like how many is too many? Does that start becoming an actual constraint? And so that's the current state of this project. So yeah, what we have is this technical infrastructure to relate selection to expected path length. But what we're still trying to build is some way to relate a system's capacity to exert selection to its ability to encode structure. And that's the sort of thing that would build an explanation for this. So it's necessarily also a very meaningful claim about what life is, if such a thing were to be constructed. So to illustrate my point, it's a bit speculative, but to say like what an explanation of that form looks like is that you have some relationship where there's a couple of observations it needs to match, right? So as people who research artificial life, we're all familiar with if you build a complex abiotic but non-living system, they tend to be very fragile. They're not very good at maintaining their current configuration. If you perturb them a little bit, their tendency is to simplify. But as organisms and as people who study biology, we also know that there is some complexity threshold beyond which a system not only has the capacity to robustly encode its own structure, but it has some surplus capacity, which allows it to actually explore open-ended forms in this combinatorial space. So yeah, thank you for your attention.